On refrigeration, the two low-stage cylinder banks compress the refrigerant to an intermediate pressure. Refrigerant at the intermediate pressure flows to the intermediate manifold. A tap off the main liquid line directly expands the refrigerant at condensing pressure to an interstage pressure in the subcooler. Liquid on the way to the evaporator passes through the heat exchanger and is subcooled. Cool suction gas at interstage pressure flows from the heat exchanger to the intermediate manifold, where it is mixed with the refrigerant leaving the low-stage cylinders. This mixing de-superheats the intermediate stage refrigerant. De-superheated refrigerant at intermediate pressure flows to the motor compartment and then through internal passages to the high-stage cylinder bank. High-stage cylinders compress the refrigerant and discharge it to the condenser. When you order compressor parts, not only will you need to know the model number, but also the serial number. The serial numbering system is identical for both the O6D, O6E, and O6CC compressors. Although the system is the same for both families of compressors, there are slight differences among current serial numbers for new compressors and service compressors. The current serial number system consists of 10 characters. As with model numbers, each character or group of characters has specific significance. The first 2 characters indicate the week of manufacture, starting with week 1 beginning January 1st. The second 2 characters are the year of manufacture, such as 95, 96, 97, and 98. The 5th character indicates the location of the manufacturing plant for new compressors, or the remanufacturing plant. The 6th through the 10th characters are where the most significant differences in new and service model serial numbers exist. For all newly manufactured compressors, the 6th through the 10th characters indicate the numerical manufacturing sequence. On service compressors, the 6th character is used to indicate the D or E family designation, and the 7th through 10th characters identify the numerical manufacturing sequence. In addition to the current system described above, there was an older system which was incorporated from January 1969 through October 1978, which you should be aware of. The older system consisted of a 7-character serial number. In it, the first character, A through M, skipping L, indicates the month of manufacture beginning in January. The second character indicates the year of manufacture within the 1970 decade, that is, 73, 74, 75, and so on. The 3rd through 7th characters identified the numerical sequence of manufacture, similar to the current serial numbering system. The 3rd character was also used to identify service compressors by replacing the 3rd digit with an X, A, or P. Regardless of the system found on a compressor nameplate, each character in the serial number represents information that parts departments must have to be able to supply you with the proper replacement parts. Internal lubrication and oil return systems. To better understand the function of the compressor and to enhance your ability to service and diagnose compressor problems, you should know how the internal lubrication and oil return systems on the O6D and O6E compressors function. Although different in size, the O6D and O6E compressors use similar lubrication systems. Oil is picked up through the oil screen and tube assembly, forced through the oil pump, and supplied to the various bearings at high pressure through internal passages drilled in the crankshaft. Pistons, wrist pins, rings, and cylinder walls are lubricated by an oil mist that's present in the crankcase. The same oil pump is used on the O6D and O6E models. It is a simple vane rotor type pump that is part of the pump end bearing head assembly. The rotor is driven by a small drive segment attached to the end of the compressor crankshaft. The oil pump is automatically reversible and delivers oil pressures above suction pressure. Normal oil pressures are shown here. The new refrigerants used with the Carlyle compressors require new types of oil. Synthetic oils compatible with the latest refrigerants are completely different than the older petroleum-based oils. The polyester oils required for the new refrigerants absorb moisture faster and in greater quantities than did the mineral oils used in the past. Care must be taken when handling these new oils to avoid contact and moisture. You must be careful when purchasing replacement oil. Of the 3 R134A oils shown here, only the oil in the center is for OEM semi-hermetic compressors. The oil on the right is for 104 mm screw compressors, and the oil on the left is for R12 retrofits. When additional oil or a complete oil charge is required, use only the Carlyle approved oils. An oil pressure regulator is used to keep the pressure constant throughout the system. The oil pressure regulator on all older O6D compressors was in line with the sight glass, so oil flow could be observed as it was sprayed from the regulator. On refrigeration systems where O6D compressors are connected in parallel, the sight glass opening is used for the oil equalization line. With the old type of regulator, oil could be pumped out of the compressor through the equalization line or float, causing a low oil level condition. On all OEM production O6D compressors, a new style regulator is positioned below the oil level, so the oil can't be pumped out through the equalization line when units are in parallel. Notice that the oil regulator on O6E compressors is on the pump end bearing head assembly. All reciprocating compressors circulate a small amount of oil with the refrigerant gas being compressed. To ensure proper lubrication at all times, both the system and compressor designs must be such that oil returns to the compressor at the same rate it leaves. Once the oil gets back to the compressor, it must be separated from the suction gas stream and returned to the crankcase sump. There are a number of ways to accomplish this. The simplified diagram shown here is typical of the O6D compressor. In the left-hand picture, at 1, the suction gas enters the compressor motor housing. On O6Ds, the motor housing is relatively large when compared to the displacement. When the gas enters the large volume of the motor housing, it moves slowly, giving the oil time to fall out and settle in the bottom of the housing, as shown at 2. At this point, we've got the oil back in the compressor, but not in the crankcase sump. Notice at 3 that there is a partition separating the motor housing from the sump. There are a number of different ways to get the oil from the motor housing into the sump, depending on compressor design. With the O6Ds, a check valve and orifice assembly is installed in the partition just below the oil level. In the diagram at the right, the venting system is used to purge blow-by gases from the crankcase. This venting system reduces the crankcase pressure so that it is less than the motor housing pressure. The small pressure differential forces the oil through the check valve and into the sump. Without the venting system, the check valve would stay closed and oil would not be able to return to the sump. The spinner tubes, shown on the right, act as a centrifugal pump in venting the crankcase and creating the pressure differential. Why then have a check valve? Why not leave a path open between the crankcase sump and motor housing? Because during startup and rapid changes in load, the crankcase pressure can exceed motor housing pressure for a short period of time. The check valve closes to prevent loss of oil from the crankcase sump. The O6E compressor internal oil return system differs from the O6D design. As mentioned earlier, the O6E compressors are considerably larger than the O6Ds. However, the motor housings are the same diameter. Although the volume of the motor housing is the same for O6E and O6Ds, the volume compared to the O6E displacement is much smaller than for the O6D. More gas must move through the same volume. Therefore, the gas velocity in an O6E motor housing will be high. The high-velocity suction gas which enters the motor housing does not allow the oil vapor to separate out as it does on the O6D. The gas and oil mist is drawn directly into the cylinders. A unique tapered oil ring is used to scrape oil off the cylinder walls and return it to the sump. Because the oil in an O6E is being returned to the sump by the rings, it's not necessary to maintain sump pressure below motor housing pressure. We do, however, vent the sump as shown in red and install an orifice in the partition between the sump and motor housing. The vent prevents excessive pressure from building up in the crankcase sump, which could cause rapid oil loss. Typically, crankcase pressure in an O6E will run slightly higher than motor housing pressure. A differential in excess of 2 psi indicates possible problems with rings, pistons, or valves. The orifice helps prevent a buildup of oil level in the sump on systems that are overcharged with oil. If the oil level builds up to the orifice, any additional oil returned past the rings to the sump will be pushed out through the orifice and put back into circulation. It's important that high oil level conditions be avoided. Severe operation and reliability problems are likely to result if the oil is above the sight glass. An O6E operating with a full sight glass will typically run 20 to 30 degrees hotter than normal. This will also draw considerably more current than it would with the proper oil level due to the slapping action of the crankshaft on the surface of the oil. This is especially true on the old-style 66 CFM and the existing 99 CFM long-stroke models. It's also possible to partially fill the motor housing with oil. This condition can cause liquid slugging at startup, increasing the possibility of mechanical problems such as blown gaskets, broken valves or rods, and so on. If the sight glass is full, oil is being forced out through the orifice, which could cause a problem. It's important, therefore, to keep oil levels within recommended limits. It's also important to use the correct oil to ensure reliability.